Earlier in the course, we derived the isentropic flow relations, which govern how changes in the thermodynamic state of a gas, its temperature and pressure, are related to each other. But what about the velocity of the flow? We know that a flow's speed is one of its most important properties, but the isentropic flow relations tell us nothing about it. In this module, we'll look at how the thermodynamic state of a flow and its speed are related for adiabatic flows. This means a flow where there's no heat transfer to or from it. To achieve this, we're going to consider flow through what's known as a stream tube. This is an imaginary tube of fluid where the sides are made up of streamlines, so there's no flow across them. We're going to apply conservation of energy in its control volume form to this stream tube. Let's examine the first term. The internal energy U plus a half V squared plus Gz is the total energy per unit volume of the fluid. If we multiply this by density and integrate over the control volume, this gives us the total energy within that stream tube. If we take the time derivative of this, then what we end up with is the rate of energy accumulation within our stream tube. The second term is the net flux of that energy through the control volume surface. Next, we have the work that's done by the pressure and the net heat transfer to and work output from the control volume. For this stream tube, we can make a number of simplifications to this equation. First, let's assume we have steady state flow. So the time derivative makes the first term 0. Second, let's assume we have no shaft work, so that work term is equal to 0. Next, we'll assume the flow is adiabatic, seeing as how we are trying to derive some adiabatic flow relations, and that means that Q dot is also going to be equal to 0. The next thing we can do is to combine the pressure work term with the internal energy in the flux term, using the fact that the enthalpy is equal to the internal energy plus P on rho. We then obtain a much simpler equation, which is telling us that the net flux of the enthalpy plus a half the velocity squared plus gravity times the height of the fluid across the control surface is equal to 0. But we can simplify this expression even further. Let's assume that our stream tube is very thin, so that the variations across the inflow plane A1 and the outflow plane A2 are 0. So we've got uniform flow across those planes. Second, for compressible flows of gases, we can usually neglect that gravity times density term. So let's also do that. So then let's look how we can simplify our integral of the flux across the control surface. We're only going to get contributions to this flux from the ends of our stream tube. This is because there's no flow across the top and the bottom. Now, because we've assumed that we've got uniform flow across those planes, basically all we need to do is multiply h plus a half v squared at A1 and A2, and then multiply them by rho times v dot n times those areas. So let's do that. So we see we've got a simple expression with no integrals. But we can simplify this even further by recognizing that density times normal velocity times area is equal to the mass flow rate. Okay, so now we've just got h plus a half v squared at each end multiplied by the mass flow rates across those planes. Now, because we've got steady flow through our stream tube, the mass flow rate coming into the stream tube must be equal to the mass flow rate going out. We're not dealing with any nuclear reactions, so there can't be any mass created or destroyed as we go through that stream tube. Now, if we make this substitution in the equation that m dot 1 is equal to m dot 2, which is just equal to the mass flow rate, then what we're going to get is that the enthalpy plus a half the velocity squared is equal to a constant, and this is known as the stagnation enthalpy. So if we have a fluid flowing with velocity v, and it has enthalpy h, and then we bring it to rest, then the resulting enthalpy when it's stationary is going to be equal to this stagnation enthalpy h naught. So you can see that we've successfully related the velocity to the thermodynamic state of the gas, at least the enthalpy. In the next module, we're going to look at how the remaining thermodynamic properties change.